Hey BC, Mr. Ellinger here with a supplemental video just to go over the stuff that we bypassed, or just to make sure, just to talk a little slower about some of this stuff. I'm going back to, here we go, to page 5 in the notes. And we skipped over this, and so I'm just going to mention it here. So just wanted to note what each one of these expressions mean. And so how would you do this? Like you kind of look at the thing and you try to decide which derivative definition is it. Like this one, I see the H in the bottom, so I know this is the F. Oh, am I going to write? Wrong pen. Yeah, wrong pen. There we go. This is the F of x plus H minus F of x over H1. And so this tells me what the function is. The function in this case was 1 over x. And so what would this limit find? What it means is this is the derivative. And it's not at a specific point because it's still just x. And so the derivative of f of x equals 1 over x. So this formula here, this limit would find you on 1 over x. Remember 1 over x from before, you know, the asymptotes and everything? This would be, if you work out this limit, this would find you what a formula for the slope of the tangent line at any x value on this curve. I'll let you know a little something, that it turns out that it's actually y prime equals prime derivative equals negative 1 over x squared if you work out this limit. You don't have to, but I'm just kind of passing it on, that you can work out this limit and you can create a formula that tells you what it's a formula for the derivative at any x value. And you can think about this curve, you know, and then the down there, is that, notice this is always negative because x squared is always positive and it's got a negative 1 on top. But you look at this curve and the slope on that curve is always negative. So it's like, oh yeah, the slope is always negative on the curve, so the derivative is always negative too, except at 0 where it's undefined, and that matches up too. All right, next one is it's the other format. It's the f of x minus f of c over x minus c. So this is finding the derivative at a specific point, and specifically when the x is 3, because it's finding the derivative at c. And so the function is f of x equals sine x. So this is the derivative of sine x at x equals 3. So not the general formula, but specifically what the slope would be at that moment. And so if you think of sine x, you know, and sine x looks like this. And let's see, pi is right here. That's 3.14. And so you're a little bit before it. You're at x equals 3, a little less than pi. And this formula would get some sort of negative number working out this limit, if you could do it. And it would give you some negative number, and that would be the slope of the tangent line at 3. Looking at this one, sometimes they use delta x instead of h's, but it's the same thing because they're just saying move over a little bit of x. So you could say, what is this one? You could pause it right now and try it yourself if you want to. But I'm going to keep going because I'm jamming this out during lunch. And so once again, this is f of x plus h or delta x, either one is fine, minus f of x over delta x. Notice delta x is going to 0. It's the same thing. Delta x just meaning change in x, a little change in x. And so the function, except it's not f of x. It's not f at, in general, it looks like it's f at 2. So it's f of 2 plus delta x. Yeah, because there's a 2 plus delta x there. And then minus f of 2 over delta x. Oh, okay, so this is f of 2 plus delta x. This is f of 2. This is just, my function here is e to the something. And so it's the derivative of e to the x at x equals 2. That's what that limit would find you. This last one, it has an f of x minus f of c over x minus c. And so I can look at it pretty quickly and realize I'm on a x cube root graph, cube root of x graph. And it's finding the slope between some point x and when x is equal to 8 because there's the 8 in the bottom. So, you know, so it's at 8. And then x is some number maybe nearby, and you're finding the slope between those 2 points. But notice that there's no limit. So this would be finding the average slope between 8, x equals 8, and x equals some x that I don't know on that cube root curve. So the goal on this is that you could see the derivative and work backwards and figure out what the original problem was, what the situation is, and what is it that you're finding. Sometimes you're finding the derivative in general, which would be a formula for what the derivative is everywhere. Sometimes you're finding the derivative at a specific number. And you just got to recognize that from what you're given. All right, that's the first thing I skipped. And then we did a bang up job of working at these ones. Now I'm just going to do the constant multiplier one for you. And so I'm just going to show you this so you can see it. If you want to fast forward a bit, this is just to demonstrate what I said was true in class. So the derivative with respect to x of c of x. So now just to do the limit thing again. Limit as h goes to 0 of cf of x plus h minus c of f of x, cf of x over h. And now I can factor out a constant out of this because the constant doesn't have any h's in it or anything. So it's the c times the limit as h goes to 0 of f of x plus h minus f of x over h. C doesn't change. C doesn't have any h's in it. So the limit doesn't influence C at all. And so that's why I can pull it out in front. And I look at this and I go, well, that's just the derivative. And so what I've shown is that if you have a constant times a function, piece of cake, just bring the constant along for the ride and take the derivative of the function. So it's like, wow, that's pretty nice. I'll leave this off right now, but if you try to do the same thing to work out what if it's multiplying, it doesn't work out very well because you can't tease them apart. Like it was really easy to separate the C here algebraically, and it's really easy to separate fractions this way, but if you try it with the product, with the functions multiplying, it doesn't work. We'll see it either next class or the class after. All right, so we've got the constant rule too. And then we had this one. So I had to do this really quickly at the end. Why don't, just for right now, I'm going to actually do this for n equals 6. You don't have to do this, but I'm actually going to work it out for what's the derivative of x to the 6th, just to show you like how this whole thing works, just to make it a little clearer. So if you're totally fine just memorizing a formula, that's not a problem. You can bypass this. But for people who are really curious, so I'm going to say x plus h to the 6 minus, I'm sorry, I interrupted myself, over h. So I'm going to do this problem, and I'm going to put in a specific exponent just to make it clear. Right? Our formula will work for any exponent, but we are kind of curious. Okay, let's see this a little better and understand it. So in theory, I have to work out this limit. So I have to expand this thing out, the x plus h to the 6th. And back in Pascal's triangle, in algebra trig, in Pascal's triangle, and limit as h goes to 0. I'm trying to write and talk at the same time. It's not always working. And so you learn how to expand these things. And so if you never saw that, you don't need to worry about it. You can just memorize the formula and you're fine. But I always like having a moment where something you learned a while ago actually is useful that you probably thought you'd never use again. I'll let you know, anyone who takes AP Stats, you're going to use that stuff in that class also. But it'll be easier than this. So anyway, so when you expand this out, it's x to the 6th, and then you have a constant times x to the 5th times h, and then a constant times x to the 4th times h. And I should just move this over so I can see a little better. And h squared. And each time the constant changes, and then the x gets 1 power smaller and the h gets 1 power bigger. And you keep doing this over and over again. And then the last one would be h to the 6th. If you want to learn about how to find those coefficients, I'm happy to reteach it. I love the Pascal's triangle stuff, and I'd be happy to show you how the formula works and how you figure out what those coefficients are, even without Pascal's triangle. And then, so that's this expanded. I didn't write every term. I kind of got bored after a while, and I just put a plus dot, 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 but that's the equivalent of what this would be, and then minus x to the 6th. Now, about those coefficients, the first one is 1, but then the ones in between, the first one was always the same as the power. So it turns out, if you FOIL this, like if you literally made 6 parentheses, and then you started just combining stuff together, you'd end up in the end with a bunch of terms that were x to the 5th to the 8th, x to the 5th times h. And how many of them would you end up with? You'd end up with 6 of them. So that's why it's 6 of the x to the 5th to the h. And then this one is bigger, though. I don't remember the numbers off the top of my head, but there's even more x to the 4th h squareds, but I don't know what that number is. But I'm just gonna put question marks there because it doesn't matter for us. And then the last one would be 1h to the 6th. All over h. The x to the 6th cancel out. Now everything has an h in it. You can come in, but I'm doing a video, so you just have to be really quiet. So all of them have an h in it, so you have to cancel out the h with the h down here. And this one loses its one h. The rest of them, everything would just get one smaller. Cool, we got everything canceled out. Let me just make it a little clearer. So what we have is h goes to 0, and we'd have 6x to the 5th, but that h is gone, fine. And then the next one, we'd have plus something, we don't know what it is, x to the 4th times h to the 1st. And then the next one, we don't know what that is, times x to the 3rd h squared, and then plus ... and eventually we get to the h to the 5th. Now there's no denominator with h in it. Just checking my time here. Oh, doing good. Now there's no denominator with h, so we can cancel out all of the h ones, because they all become 0, and every single one of these is gone. And this doesn't have any h's in it, and so as h goes to 0, this is just what it is, and it's 6x to the 5th. So notice how when it was x to the n, the derivative of x to the n, this is what we had in the notes, is nx to the n minus 1. So the derivative of x to the 6th, as example here, is 6x to the 5th. So now we have enough tools that we can take the derivative of any polynomial. Like any polynomial at all, we could take the derivative of it. Let's give you an example here. Like we gave one in class, but I made it a little simpler. Take one like, what's the derivative of 5x to the 3rd minus 3x squared plus 2x minus pi. So this would be a function. It'd be a cubic, so it's doing the cubic thing. And the question is, what is a formula for the rate of increase on this thing at each individual point? And I want a formula that works for every single point on this cubic curve, right? I want a formula that works for everywhere. And I don't want to have to do limits. Dream on! Actually, but no, dreams come true. And you can find the derivative of this thing because of the rule we gave earlier, which is when you have a bunch of things adding or subtracting, same thing, then you can just break it up into a bunch of little problems. So I can just say, I'm going to take the derivative of this, and the derivative of this, and the derivative of this, and the derivative of that. And then add them all up. So the fact that this big, long polynomial doesn't matter to us anymore. Now, in this one, I've got a constant multiplying. I got 5x to the 3rd. I've got a formula for x to the 3rd, but I don't know what 5x to the 3rd is. Well, the next rule, the constant multiplier rule, that said, if you have a constant, just bring it along for the ride and take the derivative of the function without the constant. So what's the derivative of x cubed? That's all I got to be able to do. Now, if you check out the formula here, this nx to the n minus 1, notice how the exponent that's up top, that's going to move in front. So the 3 that's up here is going to move in front and become a 3 down there. And then you've got x, and then the exponent gets 1 smaller. So it was 3, and now it's 2. And this would be multiplying. And that's all you got to do. Bring the constant along, do the derivative of the function, and then multiply them together afterwards. So I'm going to skip 3x squared for a second. And so this one here would be 2. That derivative of pi, 0. It's a constant. It's always pi. It never changes. So there's no rate of change, or 0 rate of change. Last one, 40 seconds, perfect, is what about this one? What a lot of people do is they kind of do 2 steps in one. They say, all right, so I know I'm going to multiply by -3. X squared, the derivative of that's going to be 2x. But then I have to multiply it by -3 afterwards. So what a lot of people do is they just say, all right, I'm going to multiply this thing times its constant. So it'd just be -6x. You can do it in 2 steps. You can say -3 times 2x. But what most people do is they say multiply it down and drop the exponent by 1. And that gets you your derivative. And so final answer, I could have done that in the first one, but I was just trying to show it. Final answer, 15x squared minus 6x plus 2. We just found a formula for the derivative of this cubic anywhere with no limits needed. Out of time. Bye. Bye.